We have to work with specific force field terms, and it's something I'm not going to go back into. And these sort of are the basic ingredients that you need to try to describe molecules in terms of covalent interactions and intermolecular interactions. What's of interest here, and Frank alluded to this, and Cecilia as well, is that you work with an integration timestamp that's extremely small, and then you're typically interested in timescales that are much longer, that orders of magnitude longer. And so you're looking for the emergent complexity at large timescales. Right, and so the idea is that you could picture a potential energy surface, so it might look like this in some coordinate space, and this is a high-dimensional function. And so the question is, can we use machine learning to maybe either build a more accurate potential energy surface, or more easily build an accurate potential energy surface? And something that's also of interest is making the numerical integration faster, more efficient. And so we've heard a little bit about coarse graining, so this goes into that direction, for instance. So one aspect that I'm only going to talk about kernels here, and there's one main reason that it's mainly for didactics. It's actually quite a bit simpler to look as to how the physics you're including sort of shows up in your machine learning model, and because the math is just simpler to look at. And so I'm not going to describe neural networks. There's actually a very rich and very quickly developing field of people working on deep learning, implementing physical conservation laws. Maybe Patrick will talk about this, I don't know, in terms of equivariant networks, for instance. So a lot of the ideas I'm going to talk about can be sort of translated for deep learning. It's typically quite a bit more involved in terms of the math. And so by working with kernels, I hope to try to sort of emphasize the general ideas as to how you relate sort of physical symmetries to implementing this into a machine learning model. Now I thought I'd start very simple, and so I thought we'd try to learn a simple function. And so as an application, we'd learn a Leno-Jones potential, which is a very simple model for dispersion interaction. So this is this would be a model for dispersion interaction between these two atoms. And so I want to predict the blue curve here. That's the energy as a function of the distance. I want to predict the blue curve, and then I'm feeding in these red points, right? And so I'm going to work with a kernel. So we've shown these equations already. I'm going to try to learn a one-dimensional function. It's a very simple exercise. I'm going to use this distance as a representation here. So the kernel will look like this, and then to make a prediction, and I'm going to sort of make a prediction of my energy based on these training points here. That's a sum of all training points, and then here R is my query sample here that I want to make a prediction for. And so as Frank explained this morning, you can train your model by basically inverting your kernel matrix, adding a regression term here to make it well conditioned. Fine. And so the question then shows up, what happens? So I have this, so this is actually you cannot see I'm sorry, so the underlying function is actually in dashed red, in small dashes, and the prediction is in blue, and so you cannot actually see the difference, and so that tells you that the model was able to learn the function very accurately. But then I'm going to ask the question, given that I have this model, I've trained this model, now I want to sort of abuse it or extrapolate it, and I want to predict what happens at small distances. So this is using a kernel-rich regression. And so what happens is this. And so you can see that the function goes up. So the reference function actually diverges. It goes up because of this power law here, 1 over r to the 12. My machine learning model goes up for a while, and then it hits the maximum, and then goes down, and then it goes to 0. And that's a problem. Because of course there's a whole part of the conformational space of my system that was not in the training sample of my machine learning model. And this shows in a dramatic way, in a way that the machine learning model is going to predict that at very small energies, actually my atoms are going to fuse together. And so this is catastrophically wrong in terms of the physics. And this is something you really want to avoid. And it would actually take you quite a number of training points actually to have the function diverge, because it's actually quite a dramatic behavior. And so this is the sort of very simple illustrative example to sort of motivate why we'd want to sort of encode some physics into our models, because this is very basic physics that these atoms are not going to fuse together. The Pauli exclusion principle will prevent them from fusing together. And so you shouldn't have to require much data to actually enforce this, because this is very basic physics. And so it's actually conceptually rather awkward to require a lot of data to enforce your model to abide to very simple physics. One thing I'd like to mention is that actually the function goes to 0. And one actually nice thing about this kernel retrogression is that it actually goes pretty much exactly to 0. And it's not a coincidence. It's because I've added a uniform prior here. And so the prior comes from the sort of the Bayesian scheme of the problem here, and that I'm trying to in this Bayesian framework, I'm trying to make a prediction for my function value, and there's basically two ingredients in this Bayesian framework: the likelihood and the prior. The likelihood are basically the training points I'm feeding in, and these are the red points there, and so that all my possible function values are going through these points, because I'm interpolating through the training points. And then the prior here is a space of function that I'm a priori allowing. And so if I don't have any information, I'm going to use a so-called uniform prior, which means I'm not going to provide any a priori information. And this is something that's standard in Gaussian processes, and that if you try to make a prediction using Gaussian processes, this is typically taken as a function of a mean here and a covariance. This covariance is your kernel. And then these two ingredients then form your random variable, your function value, the prediction for your function value. So the kernel is what we use in this covariance term here. This is what forms the kernel when you're solving this equation. And very often the mean term here is neglected, and that leads to this uniform prior. But that's not always the case, and there's actually some works that actually take advantage of this. And you could just, sort of going back to the example I've shown you with the Lennard-Jones, you could just say, I don't know much about my model. I just know that at small distances, I'm going to have some sort of a repulsive potential. And so I'm going to fit here or assume that I have an exponential, some sort of a repulsive function here. And it doesn't have to be very accurate, but it has to have the right behavior. And that'll mean that even if in the absence of any neighboring training points, then my model will be repulsive at small distances. And that's something that's extremely useful because it prevents you from sort of extrapolating too much. And that's been used in a number of papers. There's a number of papers by Gabor Ksenyi where that's been used. There's the recent paper on the CGNet that Frank and Cecilia talked about also used this to try to circumvent these types of issues by making sort of relatively weak assumptions as to how the model should behave at the asymptotics. Feel free to interrupt me at any time. Yes?
When you're fitting it with this prior enforcing certain points, how does that complicate the fitting process?
So practically it means that you're doing the learning around this. You're basically looking at the difference between this prior and your target observables. And so in the sort of straightforward case with the uniform prior, then you would be sort of taking the difference from function 0. So that's what a uniform prior would mean. If you use a repulsive function for small distances, then you're learning the difference from this repulsive function. Of course, what that costs you are hyperparameters, because if you say I have a repulsive function at small distances, you have to have some sort of a slope at least, and so that's a hyperparameter. And so you're making your learning procedure sort of less non-parametric because you're introducing hyperparameters. But but the key point here is not that you sort of hit the right slope. It's that you get the right behavior, and that you know that the physics tells you it has to be repulsive, and so this will go a long way into making your model robust. Because these are very high energies, and so you're very unlikely to hit these points, and so you typically don't have to be very accurate. You just want to make sure that this sort of behavior doesn't happen. So you don't want to have this barrier. Yes.
Maybe it's worth adding that energy is a little bit of a special case here, because we modeled a system like this with this energy. The equilibrium distribution is like e to the minus the energy. So if we learn an additive term to the energy that can be factored out, then it becomes like a prior distribution in the equilibrium distribution. So you basically can formulate a prior in the Bayesian sense by just an additive energy.
If it's a constant, right?
Sorry?
If it's a constant.
Just some additive function, something that you add to the energy just becomes a multiplicative factor in the distribution.
Oh yeah, right, yes,
because
yes.
Of that,
yes.
You can say this is a prior in the Bayesian sense.
Right, right.
An additive thing in the
Right,
energy.
right, right.
For any exponential
right.
family function. Yeah.
Yes. So that's sort of a simple example to set the stage as to why you might want to include some physics into your model to make it more robust. Of course, it's sort of intuitively you realize that the conformational space here that's missing from your training then has to do with sort of the part of your interpolation space where you don't have any training points that are missing and are critically missing, and so that's leading to problems into your machine learning model. So I'm going to talk about examples that go in this direction for where you try to use the fact that your system might have a number of symmetries. Because the idea will be that in general, what you're trying to do is to reduce as much as possible your interpolation space to make your machine learning procedure as simple as possible. And there's many cases for physical systems in energy landscapes and others where sort of brute force learning your system will be too expensive and you have to reduce it in some ways. And using sort of physical symmetries or physical principles allows you to reduce this interpolation space. And this is a great strategy to make sure that you will not extrapolate. And so your machine learning model will always be sort of will lead to a prediction that is reasonable. So I want to talk about the link between symmetries and conservation laws, and so that's going to bring me back a little bit to sort of very simple physics. So I apologize to the physicists, but I thought it might be useful to sort of set the stage in terms of what we're talking about in terms of symmetries, and what the consequences are. So I want to talk about the principle of least action. So we're going to define, so I'm going to talk about Lagrangian, which is the Lagrangian function is basically the kinetic energy minus the potential energy. And I'm going to talk about this object, which is the action, which is a function of a pathway or microtrajectory in your system. So your system is evolving in phase space, and so it has a microtrajectory. And so we're going to look at the time integral between between certain time t1 and t2 of this Lagrangian that may be a function of the position, the velocity, and time. And so for simplicity, I'm going to assume I have one-dimensional system and the coordinate is x. And so Hamilton's principle says that if I minimize the action, I have this variational principle tells me that the true pathway that the system will follow is the one that minimizes the action, and so x star is the trajectory that the system will take, and so that's the one that minimizes the action, and so that's really useful because that gives us a variational principle for classical mechanics. That means that we can then apply a small perturbation and then see what happens to the action. And so if I apply a small perturbation and I go from x to an x plus epsilon, and so I have for the velocity I have x dot plus epsilon dot, and I'm sort of looking at a small perturbation of the action around this sort of true pathway, so the minimum of the action. And so I'm going to have the difference between the Lagrangian with the perturbation and the original Lagrangian in the which minimizes the action. And so if I compute this, then I will get these partial derivatives, which I can then compute, and then with simple algebra you can show that if you do integration by parts, you get this equation here. And so this equation here, if you factor out epsilon, is the Euler-Lagrange equation. So that gives you a differential equation for the behavior of the system, and that's what leads to then F equal ma. Right. So by postulating this principle, you can derive F equal ma.
One more term related to the limits of Lagrangian.
Sorry, what?
Sorry. I was going to say, is there one more term which is the partial derivative of L with respect to t?
Yes, I'm assuming my Lagrangian is time independent. That's right. Thanks. All right. So let me just show you what that means for very simple systems. So let's say that now I have x, y, z coordinates, Cartesian coordinates, and then so I'm writing the potential, the kinetic energy here, and then the potential energy here might be just like gravity, right? And so what I'm going to do now is to introduce a constant translation along x and y. And so here I have xt plus x0, yt plus y0. And so if I look at what the effect on the action is, you can see that here there is no effect on translating x and y, and so that means that the action is unchanged, right? So that does not change the action. So meaning it doesn't matter where the particle is in x and y, that doesn't change my action. And so that means that this translational symmetry leaves the action invariant, and so it leaves the Euler-Lagrange equation unchanged. So this Euler-Lagrange equation is unchanged under constant translation. Right? So and if you have this, there's a number of consequences. So first of all, you realize that the partial derivative of the Lagrangian with respect to x is 0, and that's because the Lagrangian does not contain any x term. And so if you then stare at this equation, that tells you that then, so this term is 0, and so then you can compute this term, and dl dx dot here, so x dot does show up, and it shows up here. So if you take the derivative, you get mx dot, which shows up there. And the Euler-Lagrange equation tells you that because this is 0, then that means this must be a constant, because d dt of dl dx dot must be 0. Okay? And so that tells you is that the translational invariance of this system along x and y means that I have linear momentum conservation. Right? And so that means there's a direct link between a symmetry of my system to a conserved quantity. Right? In this case, the translational symmetry to the fact that linear momentum is conserved. And you can actually do the same exercise for here rotational symmetry and time translation. So here you can work it out for here would be for a central problem. For central force. So where you'd have the action as a function of a 3D vector. Here you have the kinetic term, and then v only depends on the norm of your vector. Right. So this is a central problem. For instance, if you're looking at any sort of gravitational problem. So you can do the same exercise with rotational symmetry. I mean, if you apply transformation R to R prime, where R prime is R, where you apply rotation matrix here, that would lead to this type of behavior where to R you add this alpha cross R, so then you have a vector, and then you add the orthogonal component here. You can show that for any alpha, the S of R plus alpha cross R must be S of R. And it's very easy to show from the kinetic energy and from the fact that the potential energy only depends on the norm. So it doesn't depend on this orthogonal component. And so that means that if you have rotational symmetry, you conserve, you can actually show that you can conserve angular momentum. And so this is the same argument as what I showed you in the last slide. You can just use the Euler-Lagrange equation the same way. You can do the same thing for time translation, where you apply again a transformation of r to r prime, where you take r prime of t plus a small epsilon as being r of t. So you can see you're just time translating your trajectory. And likewise, you can also show that the action of under this transform coordinate is equal to the original action, and this is up to a boundary term. So it's not exactly 0, but it's up to a boundary term, and then you can show that even with this boundary term, then this leaves the action invariant, which means that even if you apply a time translation, the Euler-Lagrange equation does not change, and so you're solving the same system. You're solving the same problem. And then you can show, and I'm not showing the algebra, but it's relatively straightforward. This is actually very nicely explained in this paper. This leads to conservation of energy. Okay, and actually these are some of the main ingredients that are going to be very interesting for us. So in general, this leads to this sort of generalizes to the so-called Noether's theorem, which comes from Noether, and that which states that for every differentiable symmetry, there corresponds a conserved quantity. Right? So if you have a symmetry, then there's a conserved quantity. And that's extremely useful, because that tells you that if your physical system has a symmetry, there will be a conserved quantity, and you can then use this at your advantage to sort of reduce the complexity of your system, because you know that there is some invariant in your system. And so a lot of what I'm going to talk about in the rest of this tutorial are sort of techniques and methods to try to sort of exploit this link between symmetries and conserved quantities. Because if you have a conserved quantity, then that means that it reduces your conformational space and it reduces your interpolation space. So for a machine learning exercise, it's extremely useful.
Can I ask a
yes.
stupid question? So you have 2, 3, 4 conservation laws, right? So you have a system with a zillion of atoms, and you're reducing dimension by, it looks like, 3, 4. Is that really a big deal? Or?
Yeah. So let's put it the other way, that you can sort of focus on extremely simple physics problems that are extremely tedious to solve in terms of a machine learning exercise. For instance, the standard, maybe I'll come back to this later, but the standard problem is, say, learning long-range interactions, and I think that's been mentioned yesterday, is an extremely difficult problem. And you can think of this by saying, if I wanted to learn electrostatics, right? So I have charges I'm placing in space. I have to be able to learn to set up a machine learning model that can take any number of particles arbitrarily in space with arbitrary charges, and then basically spit out Coulomb's law, right? And if you don't take any advantage of things like of rotational symmetries or any sort of asymptotics, it's an extremely difficult problem, and so people don't know how to solve it actually. So for this electrostatics, and this is and you'll concede this is still a very simple problem. This is just pairwise interactions, and so we're not even at a point where we can take an extremely large system and then have the luxury to say, well, I'm not going to care about these symmetries, because I think in many cases, the state of the art, what we can do with sort of learning of a physical system is not all that high. Because we actually know a lot of these symmetries. We might not know all of them, but making sure that sort of a brute force machine learning model at least satisfies all these symmetries is extremely data intensive. And then that becomes a little bit maybe controversial, because there is a bit of like two schools of people saying either I want to discover and learn the symmetries, and people saying I know the symmetries, so I don't want to sort of use data to learn them. And it depends very much on what you're trying to do.
So one example where this is very important is a consequence of energy conservation is that the force is a conservative force that can be computed through a gradient of a scalar theorem. So if you want to learn forces, the problem reduces from an n-to-n dimensional function to an n-to-1 dimensional function, which is immense.
Yeah, so I'll come back to this later. Okay, so a lot of the so a lot of the rest of this talk will be about basically looking at these aspects and how people have been trying to implement this. And interestingly, there seems to be two ways of encoding these symmetries. One is the representation, the other one is the machine learning model itself. So I'll talk about these two. And I think that the more straightforward way of going about things is to encode in the representation itself. And so that's been sort of alluded to also yesterday. So if you take, for instance, the Beta Parinello neural network, it's my one neural network example. You start from Cartesian coordinates, and then you featureize them into these symmetry functions. And these symmetry functions, so they're shown here, are only functions of interparticle distances and then angles. And so working with distances and angles directly makes them translationally and rotationally invariant. I think this is the same thing in the CGNet. And then you by feeding in this representation into your model, you ensure that your model ensures translational and rotational invariance, because you feed in these representations that satisfy this directly. The same thing was done. This is also a simple example with the Coulomb matrix, where the off-diagonal terms contain the inverse distance between atoms. And by looking at the distance, also you make things translationally and rotationally invariant. Note that there's if you use deep learning, there has been examples, I believe, of just feeding in Cartesian coordinates directly, and then sort of learning a model from the Cartesian coordinates, and that the model would learn translational invariance and rotational invariance. And this is something that typically you cannot do with kernels, because you don't have enough data and not enough flexibility to do this. And so if you're working with kernels, you have to provide a representation that encodes this a priori. Because it's very unlikely that your model would just spontaneously learn it. It just takes too much data. The other example is to encode the symmetries in the model itself. And so that means that even if I was to feed in a representation that does not carry this invariant, my model carries it, my machine learning model carries it, and so will satisfy it. And so to do this, I think it's useful to look a little bit at group theory. This is something I found in Rizy Condor's thesis. It might have come up before. I just found it in there. So I'll show you what the main idea is as to how you have a group. And so you're looking at the action of a group on your input sample as to how x is being transformed into t of x. So for instance, you could think of, again, this translation I talked about of going from x to x plus x naught. This could be this group action here. So it transforms x into x plus x naught. Now the question is, can we find a kernel, can we build a kernel or a machine learning model that is invariant to this group action? So what you want here is that your target property f of t of x is equal to f of x for any member of the group, right? That means that if I make a prediction on my translated sample, it's the same as if I make the prediction on the untranslated sample. So this is all that it's saying. So I'm making a prediction onto the sample that carries this group action, and that's the same as making the prediction on the original sample. In terms of the kernel, that means that if I take the kernel between input samples x and x prime, that should be equal. So I should enforce that this be equal to the kernel applied to t of x and t of x prime. So what I want is to build a kernel that satisfies this. And so that's typically a subclass of kernels that will satisfy this for this particular group. So I'm going to reduce the possibility of the class of kernels I can work with to only focus on the ones that satisfy this particular property. Yeah, so this example is shown here with the translational invariance. So that if I feed in x plus x naught here and x prime plus x naught, the kernel evaluation here, or the covariance, is the same as if I was working with the untranslated samples. And so the recipe in general is that to ensure invariance, what you want is to symmetrize the kernel. And so to symmetrize the kernel, very simply or intuitively, what you're doing is that your kernel is going to be a sum of all the actions in the group. Yes.
You are assuming G is finite with rotations of translation that's not true.
Yeah, so here, right, so this would be for a finite group, so this doesn't work for the translation. But then you can also,
So difficult to make it work for a non-finite group, though.
Right. So I think, right, so this is typically used for, I'll show an example for rotations. I don't know if this has been used for translations, and I don't know whether you probably get into trouble then.
So you just divide it with the integral is a problem because it's compact.
Right.
Translation, I don't know.
Right. Yeah, this is probably right. Yeah. But this mostly has come up for to look at rotational invariance.
Okay.
Tg of x,
Yes. Sorry, what?
K of Tg of x, the two packed.
No. So here this is Tg of x prime. Because you have x prime.
But also an x attribute.
No, only this is x and Tg of x prime. Yeah, this is correct, I think. This is. I can check later, but I think this is how I remember it. Well, I mean.
That's all what you demanded on this.
Right.
When your invariance equation above, you have a both. Well, it's conjugation, right?
Yes. Right, but then so that's correct. I think you get away with this by the fact that your kernel is symmetric, right?
The identity matrix will not satisfy this very right? So your kernel is not. It should be there.
Maybe it's there. This is but the idea is that you're summing over the different members of the group. So that's sort of the main idea I want to bring across. Yes.
Do you choose any group that can perform the required action, or is there a way of selecting the right group? Or maybe you can just give me an example of a group.
I'll give you. So this has been used mostly for rotations.
Okay.
So I'll just give you this example in the next slide.
For rotations, right? Is the idea that you want it's effectively like rotating one of the members all the way around.
That's right.
But it's only on one turn. Right? If you rotate both of them, then whatever arbitrary choice you gave in the original rotation sticks. So you do have to do it only.
Oh yeah, that's right. Thank you. That's right. Yes.
That was for translation either, so.
Yes. Well, I don't. So I mean, so okay. So I mean, I put this here, but this I don't think this has been used for translation. This has been used for rotations. Yes.
People sometimes just move to the center of mass and say that deals with the translation, and then only for
Right.
rotation.
Right. So one way it's been used is in the SOAP kernel, SOAP representation, where you take so you have an input sample representation. So this is a smooth density rho, and then you're looking at the overlap between rho and another input rho prime, and then you have a certain rotation matrix R onto rho prime. I'm not going to go through this equation here, but basically what I want to focus on is that when they compute their kernel, they're integrating over all rotations of this overlap distance between rho and rho prime of the rotation matrix R applied onto rho prime, and they do it only on this one. You need to get, because you fix one sample and you rotate all the other, you rotate the other one around it. And what you typically would do indeed is that you first translate so that their center of mass overlaps. And that's a way to get rotational invariance into your kernel. And that's been a way to then extend this to not just to invariant properties but to covariant properties. And so there's a slight but important difference between these two concepts. So an invariant property means that say I have this water molecule. An invariant property might be if I have it in the gas, non-interacting with anything else, it might have an energy. And so I could rotate this molecule and then the energy would still be the same, because there's nothing else around it, and so there's no reason why the energy should change, right? So in that sense, the energy is invariant to the rotation. If I look at something like a force acting on this molecule, or a dipole moment, for instance, so this is a vector quantity now, and that means that if I rotate the sample, then the force should rotate with it. And so that becomes covariant. So you can see it here. So if I rotate my water molecule, then my target property needs to rotate as well. So what you want now is this dipole moment not to be invariant to rotations, but covariant to rotations, as to how the sample rotates with the target property. And so in this particular case, sort of building building this covariance property into the machine learning model has been extremely useful. And I actually don't know of any example of the first approach of instead doing this with the representation. So typically you have to work with the machine learning model. So you have to build this covariance into the machine learning model. Oh, actually, that's not true. I know a way. I can come back to that later. So it's the same exercise. So you have one to make say a prediction for a force or a dipole, so any sort of vector property of your molecule, of your sample. And so what you're doing is you're going to take your sample with your representation rho, and apply some sort of a symmetry operation S, like a rotation. So I'm going to apply a rotation S, and what I want to enforce is that I could this be equal to my prediction onto the non-rotated sample, so the original sample, but then I apply the rotation onto the prediction of this dipole moment. Right? Because I told you the sample, the target property rotates with the sample, so it doesn't matter if I rotate the sample and then make the prediction, or if I make the prediction and then rotate it. And so that's the sort of the condition I want to enforce. And so the way to do this is to work with a sort of a subclass of kernels that enforce this, and which are called covariant kernels. And so covariant kernels, again, would so in this sort of similar spirit, would work in the following way: that a covariant kernel would mean that if you have a certain sample rho for which you apply rotation S, and another sample rho prime for which you apply a rotation S prime, then you could that should be equal to this expression here of having the original kernel on the unrotated sample rho and rho prime, and then you apply the rotation matrix S on the left side and the transpose of the rotation matrix S prime on the right side. And so that's, again, a condition you want to enforce to make sure that you have the correct rotational properties of your kernel between two samples. And so working sort of, if you can ensure this relationship, then that is equivalent to what I've shown you in the last slide in terms of having the prediction sort of rotate with the sample. And so what's been interesting recently, and so it's very nicely described in this paper, is sort of the way of building a kernel that a priori satisfies this relationship. And what you have is, again, working with a subclass of kernels that satisfy this. And because they're doing this with kernels, they can actually work this out and derive this analytically. And here the same idea I've shown you before applies in that this kernel here, again, is an integral over all rotations of this original base kernel between rho and rotated rho prime. But the difference with what I've talked to you before, which were about invariant properties, is that here I'm multiplying by the rotation matrix R. So that makes it covariant, because it rotates with the sample. And they can actually integrate through Euler angles analytically for a simple class of Gaussian kernels. And what they come up with is an expression that looks like this. And so what I'd like you to focus on is, so this is sum over I and j. These are interparticle distances. So an example is shown here. So I would have one sort of interparticle distance here, Ri, and then another one, Rj. And then what this object is doing here is this is a prefactor, and then this is an outer product between Ri and Rj. So it's looking at the alignment between the two vectors. And what's really interesting is that sort of geometrically it has to be this, in the sense that here what this is you sort of went from a scalar-based kernel, which means a kernel entry is only a scalar. So the similarity between two samples is a scalar quantity. And while this covariant kernel is a matrix-valued kernel, so it's a 3x3 entry. So if I'm looking at the similarity between two samples, it's a 3x3 matrix. And the only way really of building this matrix-valued kernel from these two vectors is just by taking an outer product. And that's really interesting because it tells you that what makes this covariant is not this prefactor, it's this term there. And so what you could probably do, and I don't think that's been tried out, but what you could probably do is sort of throw away this prefactor, but keep this. That's the essential ingredient. It might affect the performance of your machine learning model, that I don't know, but this covariance property would still be there. And that's really interesting, I think, because this is a relatively simple example where you can actually integrate and derive things analytically, but there might be other problems that are more complex where you might not be able to. But you might still be able to sort of reason in terms of geometric arguments and sort of try to figure out, depending on what the geometry of your system is, how your kernel has to look like. So more recently, we've extended this to not just to vectors, but to second-rank tensors. And I'll show you an example in a minute, but we've used this for quadruple moments. And the idea is very much the same. But of course, the math is slightly different as to how, if you're looking at, so this would be a kernel for quadruples, so for second-rank tensors. If you apply these two transformations, S and S prime on rho and rho prime, then you have more complex sort of sequences of rotation matrices that you have to apply. It also makes the math a little more nasty because now you have this is a second-rank tensor, and so these are for what you end up with is a 9 times 9 entry for one kernel element. So it's pretty nasty. But the idea is the same, and so you also have these geometric features that show up. Any questions? Yeah.
What can you say about the feature spaces associated with these kernels? Do you have also some additional structure or properties?
I'm not sure. I'm not sure. My feeling is that so I would tend to guess that it doesn't, because we don't change representation. As long as you don't change representation or sort of the baseline, the baseline features of your kernel, then you should get to similar feature space. It's sort of just restricting. It's enforcing your model to abide to these rotational symmetries, but I really don't know. Okay, so I'll show you an example of how we use this in terms of intermolecular interactions. So I'll show you a quick example where we're interested in sort of trying to learn intermolecular interactions. This is what I was mentioning at the beginning, for an arbitrary sort of for a large number of molecules. And so one thing that was of interest for us is to look at this for, not just to learn this for one particular molecule, but to learn intermolecular interactions for a large number of molecules. And again, because of reasons I mentioned before, in terms of some of these things like electrostatic interactions and other types of interactions I'll show you in a second, it's not exactly clear how to learn this, how to learn interactions at long range for an arbitrary number of particles. And so what we did instead is to sort of resolve into using a traditional sort of physics-based force field, but then learning the coefficients. And then the coefficients would depend on the chemistry of the molecule and then the configuration. And so the structure looked sort of very similar to a standard polarizable force field, in that we'd have a number of sort of functional forms that we know from the physics, and then but then of course these provide the functional forms for these different interactions, but they don't give you the coefficients. Coulomb's law tells you how your electrostatics decay is a function of distance, but it doesn't tell you what the partial charges you should use for a particular molecule. And so for these coefficients, then, so then for these, you can sort of like think about these different interactions in terms of two different physical types of schemes, one being perturbation theory at long range, and then at short range, you could think of overlap models. And perturbation theory is an extremely elegant framework to derive a number of classical intermolecular interactions, and then overlap models are very useful way to try to compute short-range interactions by modeling them in terms of the overlap between atomic densities. But so that would mean that in this scheme that so the physics would tell us how these things scale, but then we'd have to use, we'd have to parameterize all the coefficients for different molecules. And so you could run, say, electronic structure calculations for a given molecule to get these parameters, and then you do this for many molecules. And what we'd like to do is to, instead of set up a machine learning model across all these molecules, so that next time we use this framework, we don't have to actually run an electronic structure calculation, but we can just predict the coefficients for any molecule and any configuration. And so that was the idea, that we'd sort of use these different terms here. So we learn different parameters, so multiple moments, so for the electrostatics, atomic densities for the overlap models, and then Hirschfeld ratios for the dispersion and the polarization. And so I'll show you this in terms of the multiple moments because they link to these covariant kernels, in that you can expand the electrostatic potential. You can expand it in terms of this series here, and then you get a number of terms, and then you have here a charge, a dipole, and a quadrupole here. And these give you more anisotropy in describing your electrostatic potential. So using a charge only is very symmetric, and then as you go to higher moments, you can describe more local anisotropic features. And so they allow you to more accurately represent your electrostatic potential. And of course, one challenge was that these dipoles and quadrupoles rotate with the sample, so we had to make use of these covariant kernels. Again, along these lines of the complexity, even sort of learning, say, the force, of the dipole moment of a water molecule, and if you'd have to feed in all possible orientations, is extremely costly. So this is something that blows up immensely, and something you don't want to do. And so it's really important to encode this. You really don't get anywhere if you don't encode these rotational symmetries. So they might not be enough, but clearly if you don't apply them, you will not get far. And then what you find when you look at learning curves, these are for charges, dipoles, and quadrupoles, that in general it's a lot easier to learn lower moments, which makes sense because they're simpler objects. It's also interesting in terms of the chemistry is that you typically it's easier to learn terminal atoms than carbons and nitrogens, and that's probably because of the valency. You can see this also by looking at correlation plots. They actually don't show very well here, but they look worse than they actually are. That there's a huge concentration of points along the diagonal, and this is not really represented well. But so in general, it works well. There's of course a few outliers where we could do better, but for a large number of geometries and compounds, it works very well. And so what that means that we can then use it and apply it to a large number of molecules, and then sort of make predictions for intermolecular energies, and then we get very nice correlation with coupled cluster data. And of course the prospect, this is more for people doing building force fields, is that here you end up with a handful of parameters, and this is across the sort of chemical space of these small organic molecules. Whereas if you think about the traditional force field, it's typically hundreds to thousands of parameters, and so that makes your model almost non-parametric, which is extremely nice. Okay, so I'll spend the last yes.
Can I ask a quick question? So when you learn those dipoles and quadrupoles, are they atom-centered? Are they the quadrupole of the hydrogen atom in a given environment?
Yes, that's right. So you take an atom, right? You take an atom, and then you look at its environment up to a few angstroms. So you'll take maybe like 6, 7, 8 atoms around, and then you look at its local environment, and then your prediction is a function of this local environment.
So in other words, for the molecule, it's just the sum of all the atomic contributions.
Yes.
Similar energies, etc.
Yes, that's right. That's right. Yes. So if there's no other question, so I want to spend the rest of this tutorial on energy conservation because it's become quite an interesting and active topic in the last couple of years. And is also something that's extremely important to ensure. So I want to spend a little bit of time on this. And so typically when you're learning a scalar field, so you have a certain property f that may live in Rn. So if you're in 3D, so that would be R3, and you're making prediction along R, right? So if you're making prediction of the energy, say, then you're making a prediction that lives in R. That means that your weight coefficient here also for a certain training point I lives in R, and your kernel takes the product between two samples that live in Rn and then map this into R. right? And so when you think about sort of doing the matrix algebra, you have your target properties here. Here you have your weights, and then here you have a kernel. And so if you're trying to work with a vector field, so you say you're trying to learn a force, you're mapping Rn into Rn. And so the simplest thing you can do is that you simply sort of scale up the number of parameters that you have. So your number of optimized weight coefficients for each training point I now would live not in R but in Rn. So if you're in 3D, then you have you have 3 values. And your kernel now, for looking at the similarity between 2 samples, would now be a matrix of size small n times small n. Right? So this is what I told you before with, say, with the covariant kernel, where you went from an entry for a kernel that was scalar, so it was size 1 by 1, to a kernel, a matrix valued kernel that, so for each sample you would have, for each comparison between samples, you'd have an entry of size 3 by 3. And so that naturally sort of blows up your matrix algebra by a factor small n, so the sort of the dimensionality of your vector field. And so that's sort of the default way of doing this, which means you're not putting any prior in the vector field. So you're learning all the components independently. And that's a bit of an issue again, or sort of a missed opportunity, because you know that your force field is energy conserving. And so if force field is your energy conserving, that means that it must be curl free. So the curl of the force must be 0. And so what you would like, again, and this is again in the same idea as before, is that you'd like to design a kernel that is also curl free. So if you work with a subclass of kernels that enforces this curl-free property, then you can be sure that you will have a force field that is energy conserving. And so what people have worked with are going to skip the details here, but you can look at this in terms of radial basis functions. You can basically think of applying a linear differential operator to your kernel. And so what we're going to do here is as an example, for instance, is that we'll apply the Hessian, so the second derivative, the matrix of second derivatives of your kernel, and so it'll look like this. And so what I'll show you in a couple slides that this applying this linear differential operator actually leads to an energy conserving force field. And so this is just an example of so people try to learn a vector field. So from number of input samples here, made a prediction. And then what they've done is what they can do is sort of separate this into a divergence-free part and a curl-free part. And the way they do this is by sort of working with kernels that have these different structures. And so imposing these structures onto your kernels make sure that your resulting vector field is either divergence-free or curl-free. So this is really useful for, say, building a force field. That is really useful, say, for building, for instance, a magnetic field. So I wanted to try it, and so I've worked out a little toy model. And so I've taken the potential from again from the CGNet paper, which is shown here. So there's this toy model which is in 2 dimensions. I think Frank showed it this morning. And so in the CGNet paper, what they do is that they take this, so they run Brownian dynamics in this 2D potential. And so, for instance, if you were to run, so if I run Brownian dynamics, then the distributions might look like this. And you can see that it's actually not very good, so that means I haven't run it all that long. And I've done this on purpose. Just bear with me. But so I have a particle living in this landscape. I'm just running Brownian dynamics. So in the paper, what they did was to sort of marginalize the y-axis to only build a coarse-grained force field that's only resolved along x, right? And I'm not going to do this. I'm going to stick with the original x and y, so the two-dimensional landscape. But I'd like to build a machine learning force field from input samples. So I'm running Brownian dynamics, and once in a while I just record the force I get of where I am, and then I'd like to learn that. That's the reference data for the force field. So if I differentiate this function here, that's what I get for the x and the y components of the force field. And you can see that you get the right features in that. So there's two minima along x, and so these are shown here in the dark and the light region. And then along y, it's basically a single well, and so you get something that's roughly linear along y. But then on top of that, you get a lot of ringing effects, a lot of very sort of high frequency effects, which are due to this sine function, and then would sort of get amplified in the derivative, which make the learning a little bit more difficult. Okay, so first I'm going to do I'm going to compare two ways of building a vector field. So one will be the standard way, sort of like the naive way of sort of just learning independently the components, and then the other one will be to sort of use to build a machine learning model that is energy conserving a priori. And so here I start by learning f of x and f of y independently. So I'm setting two machine learning problems here. And so learning f of x here, sort of any information I get about the contribution along x does not affect at all my machine learning model along y. So they're completely independent. So I'm working out two different machine learning models. The only twist I'm using for this problem, it'll get clear later, is that I'm actually not working with x and y as a representation, but I'm using these two sort of rotated axes, which for this particular problem doesn't make a difference. I'm just rotating here my reference frame. And so I'm setting up here these two problems along x and y, and I'm solving them. So I'll show you the result in a second, but I also want to compare with an energy conserving kernel. And so the way you can show how the kernel comes about is the following: that I want to build a kernel between two forces which are energy derivatives, right? And so a kernel is a covariance matrix, and what's useful here is that the derivative here is a linear operator, so I can take it out of this covariance matrix. And so that's what I do here, in that here K is my kernel between inputs Qi and Qj, so Q are my representations. I have this, and then because of the chain rule, then I have to take the derivative between, so the partial derivative between my representation and then the Cartesian coordinate of sample I and component K. Okay, there's a bit of index to keep track of. And so this is between sample I and sample J, and here I'm looking at the energy derivative with respect to the component K, and here with respect to the component L. And so I get this term, and I get that other term, which is the other term that you get because of the chain rule. So this term is the Hessian. That's what I showed you in a few slides ago. And you can actually work out with the Hessian is, say, if I'm using a Gaussian kernel here, so you can work out this term. So just calculating the partial derivatives is very simple. What you get is this. And there's several messages. So here basically this is the original Gaussian kernel that I had, and then I just have a certain prefactor here. So that's the only thing that changed, right? So first thing, everyone in the literature seems to ignore this, and I think that has to do with the fact that this term is not essential to have the curl-free part of this vector field. It just comes out sort of, it comes along for the ride because as a result of this derivation, but it doesn't actually ensure energy conservation, and so this is not something that's actually very useful to encode. And so people haven't been using it, at least I haven't seen any paper where they've used it. What seems to be essential is this term. And that's because that's the term that allows sort of the partial derivatives of the representation. You see it's a scalar product between component k and L, and so it allows to communicate information between components. So I told you before, I can in sort of the naive way, I can just learn the x and y components independently. What I would really like to do if I want to make my vector field curl free is that I need to have some information between x and y. So there needs to be some propagation of information. And that seems to be the important part here, this scalar product. And which is why I use this representation here, because if I use x and y, then dq dx and dq dy you see do not talk to each other. So they're orthogonal. That's not what I want, because then I'm back to the independent problem. So that's why I'm using this sort of this rotated frame, because this way these two derivatives are not orthogonal. Okay. So this is a learning curve for learning this vector field. So I'm looking at the force as a function of the number of training samples. And I have two curves here because I'm training I'm trying to predict f of x and f of y. So the x and y components. These are the references, and then these are sort of predictions for x and y for the independent model. So I'm not doing, this is not an energy conserving force field. And I'm purposefully looking at this particular, I think this is like 50 samples here. So I'm working in a regime of low data. So I'm not looking at these examples here, but I'm looking at low data. And you can see it's actually not particularly good. You can see this is very light in this region. This is a little bit better. And you can see actually that f of y is a lot better than f of x, because f of y, along y, you just have a simple harmonic potential, basically. And so it's a lot easier to learn. And that's why there's so much of a difference between the x and y components. If I compare with the energy conserving force field, it ends up here. So asymptotically, it gives you to about the same behavior, and that I think it has to do with the fact that in the end, you're using the same representation, same kernel, or same type of functional form for the kernel, and so you will get at large enough data, you will get the same behavior. What's interesting is if you work at low with low data, and you can see with low data here, the performance is a lot better. And the variance is a lot smaller than some of the independent models. It's actually not as good as I was expecting it would be, and that might just have to do with the fact that the dimensionality is so low. But in the end, if you compare sort of the models, again in the low data regime, this is independent components, and that's the energy conserving force field. And you can see that, so while the ringing effect is gone, of course, because it's totally smooth, this feature here, well, features between the light and the dark regions are a little better described there. So there's a little bit of an improvement. Which again is sort of one of the messages that it allows you to make, of course, if you work in a regime where you have sort of infinite data or sufficiently many data points, it doesn't really matter whether you a priori satisfy energy conservation or not, because your model will have enough data to figure it out. What's useful is that if you work in a very sparse regime in terms of number of data points, then you work with a class of machine learning models that ensure energy conservation, and so your prediction, whatever it does, will ensure energy conservation. And that typically means that you end up with a model that's a lot more reasonable. that's been used in a paper by Klaus Robert Müller and Alex Tkachenko, where they implemented this, and they could use, actually they could reduce by using energy conservation, the way I described it, and then on top of this using some local permutation symmetries, they could reduce enormously the number of training points they needed, so that they could afford doing couple cluster calculations to, say, learn a potential energy surface for a small molecule. And that's the interesting aspect, that you can, if you encode enough physics that allows you to reduce enormously the number of training points you need to make a reasonable prediction, and so you can actually work, you can actually make significant computational savings. Anatol told me yesterday that they've published a better version of this, which would reduce the dimensionality of the matrix valued kernel, but I haven't had time to understand it, so I'll just flash it. And so I want to conclude here as to how so there's a tight link between your phase space, your conformational space, and sort of like dark regions of conformational space you may not be able to or have had the chance to sample, which directly link to the interpolation space of a machine learning model. And a lot of the advances in the field has had to do with trying to build in symmetries to try to alleviate this risk of going into regions where you haven't actually sampled yet, and you're extrapolating your model. And so that sort of calls for using all the symmetries that you know of and you can take advantage of, to working with a class of either kernels or neural networks that a priori encode these symmetries so that you don't have to learn them, but they satisfy them a priori. Thank you for your attention.